Okay, this is 6C. We're looking at three new terms to use in reference to networks and matrices. We will learn about isomorphic graphs, connected graphs, and adjacency matrices. And let's start with isomorphics. The point about an isomorphic graph is that it has the feature that each vertex has got the same connections with other vertices. They look completely different, but they are in fact the same in that sense of isomorphic, iso meaning same. Now basically, to check if two graphs are isomorphic, you have to look at all of the vertices. These have all got 4 vertices. They're all labeled A, B, C and D, but you have to check, for instance, that if graph 1 and 2 are isomorphic, then there has to be a connection from AC to AD direct, and which there is. There has to be a connection from BC to BD, which there is. There has to be a connection from C to B, C to A, and C to D, which there is. Also, obviously, from D to C and B and A, which again there is. This is not recommended in the textbook, but I think it's a good idea. You actually list all the connections for graph 1. So we have a connection A to C, A to D, B to C, and B to D, C to D, which actually covers all the connections. You don't have to list them all twice, and then check what we've got on this one and make sure that they match 1 to 1. So is there a BC on the second graph? Yes, there is. Is there a BD on the second graph? Yes, there is. Is there a CD? Yes, so those two are isomorphic. Then we do the same for the third graph and find that there is no problem. They are all isomorphic. What about graphs that are not isomorphic? Again, on the face of it, they might look as if they are isomorphic, but if we list the connections for the graph 1 as on the screen, and then start listing the connections of the second graph, yes, there's an AC, yes, there's an AD, but no, there is not a direct connection from B to C. So that has already identified the fact that graph 2 is not isomorphic with graph 1. Have a look at graph 3 and start listing its connections. Yes, AC, yes, AD, yes, BC, but there is a BD, yes, but no CD. So no, they are not isomorphic, graph 1 and graph 2 and graph 3. Okay, let's move on to connected graphs. The point about a connected graph is that you can, one way or another, doesn't matter how, get from every node to every other node, which is another way of saying that there are no isolated vertices. It doesn't matter whether you have to go through a vertex to get to another vertex. The point is, can you get from, in the first one, to everywhere else? Yes, you can. On the second one, you can go from A to C, you can go from A to D via C, and you can go to A to B via C and D. That's no problem. So those 3 graphs are all connected. Disconnected graphs, well, graph 1 has an isolated vertex at B, so you can't get to B from A, C and D along any given path. Secondly, graph 2 has a isolated vertex at D. Third one is there's no isolated vertex, but the 2 graphs are actually not connected. AD does not have a connection with CB. So those are 3 examples of disconnected graphs. You can connect 2 graphs with bridges. That's another technical term. There is a bridge in graph 1 at CD, because if you remove CD, you have a disconnected graph. On the other hand, if you removed AB, you would not have a disconnected graph. So CD is a bridge. Looking at the second graph, you can see that if you remove CD, you now have a disconnected graph. These are just technical terms to get used to using. CD, the bridge, highlighted in red. Okay, moving finally to adjacency matrices. You've met these before perhaps in year 11. Every network has a corresponding matrix. This network has 5 vertices, so the matrix has 5 rows and 5 columns, and a 0 means that there is no way of getting from A to A, which would be a loop. There is one way of getting from A to B, another from getting to A to C, no way of getting from A to D directly, and A to E there is one way, and so on. Notice there is a route from B to C. There are 2 routes from B to C, so that is a 2. Note also that there is all zeros on the leading diagonal, which I'm just drawing now, which means that there are no loops. And you could also notice that the matrix is reflected about the leading diagonal. So AB is a 1, BA should be a 1. AC is a 1, so CA should be a 1. BC 2, CB 2, and so on. So when you want to come to draw the network from the matrix, you only have to use one side of that leading diagonal plus the diagonal itself. Let's try that. So as I just said, if you're going to draw a network off a matrix, notice that the matrix is mirrored. You only have to do some of it. How do you identify loops? Well, there's a loop on this one because there is a 1 in the D to D element of the matrix. Note also how you would identify a disconnected graph if there was one. That would have row A and column A, for instance, all zeros if A was disconnected. If E was disconnected, then row E and column E would all be zeros. Try to draw it planar. That's a word that's coming up soon. There's the leading diagonal again. Try to draw it planar, which means no crossovers. We'll see more of that in the next exercise. Planar means no crossovers. So on the next slide we'll try and draw it. Those are the notes again at the bottom. Matrix is mirrored. Now, there are 5 vertices. I suggest you draw them in a circle shape in alphabetical order. Makes it easier to mark as well. So we have 5 vertices, A, B, C, D, and E, and then reading across the top, there are 2 connections between A and C, so they will be the first things that get drawn. There's one of them, there's the other. There's a way to get from A to E as well. B to C has 2, so we'll put those in. B to D also there is 1. Now no crossovers, so go around the outside. We've done CA and CB already, so let's just look at CD, put in a connection there. There is just a loop at D, and that is it. Here is your exercise, 6C, pages 214 to 16, all questions, and you should now be able to demonstrate you can distinguish and name isomorphic and connected graphs and work with adjacency matrices. That is your success criteria. Thank you.